Welcome back. We're about to start the final unit in this course. This time, we're mostly going to focus on review and some practice problems to get you ready for the exam, or at least to get you in the mood for the exam. But there may also be just a little bit of fun. You may get the chance to hear someone who is not Wes Weimer talking. I know. Someone with real voice inflection? Be still your beating heart. But before we get going with practice problems, let us make the list. A high-level summary of everything you've learned thus far. We started off by introducing the concept of a language as a set of strings. Regular expressions, finite state machines, formal grammars, these all denote or accept or correspond to sets of strings. In fact, the set of all valid JavaScript programs is just a set of really big strings. One of the first tools we introduced was regular expressions, which are just a concise notation for specifying some sets of strings. Those sets of strings are called regular languages. An incredible surprise move, regular expressions denote regular languages. And we learned a bunch of regular expressions: plus, star, disjunctive choice, ranges of letters, 0 or 1 copies. And we ended up using these to specify tokens. More on that in just a bit. Then we learned about finite state machines, which are a cool way to draw regular expressions. And also, it turns out, a way that we implement them under the hood. That's how Python actually does it. And here I've shown a finite state machine for AB star. Possible to have ambiguity or epsilon transitions in a finite state machine. That makes a finite state machine non-deterministic, because if you're trying to simulate it, you don't know exactly where to go at any given point. It turns out, however, that is not a problem at all. We can convert non-deterministic finite state machines down into deterministic finite state machines. They make it a little bit bigger, but it'll totally work. Then we moved on to the more powerful context-free grammars, which are a concise notation for specifying some sets of strings. Wait, I thought that's what regular expressions were. Actually, they're both just concise notations for specifying possibly infinite sets of strings. And your typical context-free grammar is just a set of rewrite rules with a non-terminal symbol on the left, an arrow, and then some terminals and non-terminals on the right. And terminals are the same thing as tokens. They're the actual input that we're trying to match. And there's some cool things that we can do with context-free grammars, like matching balanced parentheses, that we could not do. We're certain we cannot do it. It is impossible to do correctly with regular expressions. We often want to check and see if a string is in the language of a context-free grammar or matches that context-free grammar, can be derived or generated by that context-free grammar. These are all the same question. And one way to do that was memoization, which for many years I always wanted to call memorization, but it's just not. It's also called dynamic programming, which sounds really exciting, but in practice basically builds charts where we write down previously computed results so that we don't have to compute them again. This is called being lazy, and it's a phenomenal virtue when you're writing programs. We can combine context-free grammars and potentially memoization together to get parsing, which is the process of determining if a list of tokens is in the language of a context-free grammar. If so, we produce a parse tree. Where did we get that list of tokens, you ask? The process of lexing breaks a big string, like a web page, up into a list of tokens or important words. The tokens are specified using regular expressions, which means that a lexer is implemented using finite state machines. We do lexing first and then parsing. I have written them out of order to shake things up. Once we have our parse tree, we're getting closer and closer to the meaning of a program. One aspect of program semantics or program meanings is the notion of types, that we can classify objects or values like 1, 2, and 3 into groups and say, those are all numbers. So a type is just a set of values and some associated operations that you can apply. So the values might be things like all numbers, all strings, or all lists. And the operations might be things like plus, minus, divide, or length. I can apply length to a string or a list, but not a number. I can add numbers, strings, and lists, but it means something different every time. I can divide numbers, but I can't really divide strings or lists, at least not using this division operator. Types are our first step along the road to meaning, and in computer science, we formally call that semantics. By the way, if you've been wondering the whole time, semantics is a tricky word that essentially always ends in an S, even when we're using it in sort of a singular fashion. Semantics of a program, its meaning. What does it compute? A program may have type errors, like if you try to divide a string by an integer, or it may have any number of other exceptions, but in the general case, it produces a value. This means that we have computed something. That was the result. That's the meaning of our program, just like a sentence in English or French or Cantonese might have a meaning. Once we have a grip on semantics, we can introduce optimization, where we replace one program with another, or conceptually, one part of a program with another, as long as the whole thing has the same semantics. This is the critical rule of optimization. You can't change the meaning of the program. If you can't change the meaning, what can you change? Well, typically the new code you've brought in uses fewer resources, less time, less memory, consumes less power, and we've seen a bunch of examples of these. X times 1 could be replaced with just x, but x divided by x cannot be replaced with 1 because in the single case where x is 0, this changes the meaning of the program. After optimizing, or not, you never have to optimize, we can move on to interpretation. This is the fun part. We recursively walk over the parse tree, and the meaning of a program, the final result, the picture we should display for a web page, the result of a computation in a financial program, is computed from the meanings of its subexpressions. So if I'm in a state or environment where A maps to 5, I can compute the meaning of this abstract syntax tree expression. Well, plus of times and plus, I'll go down here and figure out what A is. A is 5, 3 is 3, I multiply them together, I get 15. Over here, 1 and 2, I add them together and I get 3. The whole thing, I get 18. Walk down the tree on both sides, and only as I'm coming back up do I compute the values. Typically, to perform interpretation, we have to track state, like the values of variables which may change, in environments. And environments are often chained together, especially as you make function calls. Finally, we put all of that together to build our web browser. We followed a particular architecture. You could imagine doing another one, but this is the one we used for this class. We start by lexing and parsing HTML, treating any embedded JavaScript as a special token. Our HTML interpreter walks over the HTML parse tree, and whenever it gets to this special JavaScript token, it calls the JavaScript interpreter, which just returns a string. We got the string from a bunch of calls to document write. The HTML interpreter gathers up all the words in HTML or words computed by JavaScript, and just calls the graphics library to display them. Wow! And then we're done.